Hi, everyone. Welcome back. Uh, Fortunately, we're all done with all of our quantum theory material that we're going to go over for this unit. So we're going to move into our very last topic for the unit, which is the periodic table and periodicity. So we're going to take a look today at how the periodic table is set up and some of the trends and things that elements have in common. So let's go ahead and jump right into this today. So our first thing that we'll look at here is the person who started building the periodic table and organizing the elements by similarities that this person found those elements to have. And this gentleman, Dmitry Mendeleev, was the first person to start organizing the periodic table, and he did this some time ago, back around 1869. And he was able to do this because he noticed periodic reoccurrence of physical and chemical properties, meaning he noticed that different elements actually had similar chemical properties and behaved in a similar manner. So he was able to place those elements in next to each other due to the fact that they had these similar properties. Mendeleev didn't have all of the information, and not all elements that are on the periodic table were discovered back in the 1800s. But Mendeleev was wise enough that he left blanks for elements that had not yet been discovered. The trends that he was able to recognize allowed him to notice and plan for elements that had yet to be discovered. So he originally arranged elements by their atomic mass. And if you take a look at the periodic table today, the elements are not, in fact, arranged in this way anymore. It's no longer by increasing atomic mass. It's close. If you take a look at the periodic table, you may want to go to do this. See if you can find somewhere where the mass does not increase. We know today now that the elements on the periodic table are arranged by their atomic number. So Mendeleev had a little bit of information. Here's some of the elements that he was able to put into his version of the periodic table. Okay, so not a comprehensive list. Obviously, a lot of elements had not been discovered yet. So here's kind of how he might have arranged these elements. We see a number of them, and we see a number of holes that he left open. These particular elements had not yet been discovered. However, because of these similarities that he found amongst different elements, he knew that there had to be some element that just had not yet been discovered that could fill that space. It wasn't until Henry Moseley in the 1900s used X-rays to determine the atomic numbers of the element. As we know today, now the periodic table, the elements are arranged by atomic number. So he was an English physicist, and he determined nuclear charge of those elements. Okay, that nuclear charge, remember those protons and electrons, okay, are charged particles, but in the nucleus, it's the protons that give the positive charge, and it's the protons that tell us the atomic number. So he built off of Mendeleev's theory and arranged those elements in order by their atomic number, that number of protons in the nucleus of that element. Okay, just a little side note here, Henry Moseley was killed during World War I at the age of 28. So this British scientist didn't get to continue building off of what he had started. So as a result, Britain no longer assigns scientists to combat duty in times of war. They find them to be pretty valuable doing other things for us. So the periodic table today is arranged, as we know, still by atomic number, okay, the number of protons in those elements. And it's arranged into rows and columns according to those similar properties. So we're able to group those elements together based on those similar properties. And again, by increasing atomic number. So we follow what's called the periodic law, okay? When elements are arranged in increasing atomic number, there's a repeating pattern or a periodic pattern that share similar chemical and physical properties. And we'll get into some of these chemical and physical properties as we go through this today. So the organization of the periodic table, let's talk about those periods or those rows. Okay, those are horizontal rows, and they're numbered 1 through 7. You might remember this a little bit from when we were talking about atomic theory earlier in the unit. Okay, this is also known as the series. So elements that are in the first and second and third series and so on. Also, the elements are arranged in groups, and groups are vertical columns. So sometimes you might hear me referring to those as column 1 or column 2, also known as group. So group 1, group 2, and we'll go into some examples of these as well. Also known as families. So we did a worksheet where we looked at some of these different families. So just know that families and groups and columns kind of all the same thing there. So, and they're usually named by a number and a letter. And we'll get into the groups on this here as we go. So 1A, 2A, 1B, 2B, and those are we're talking about the inner transition elements and things like that. We'll get into that. So 1A through 8A are the representative elements. And as we take a look at a periodic table, we'll notice that those are the elements that fall into the S and P blocks on the periodic table. Groups 1B through 8B are the transition elements. Those transition elements fall into the those inner transition metals, the D block. So the two bottom rows, okay, are known as the rare earth elements. We don't necessarily assign a group number and letter to those, but they're just known as the rare earth elements, also known as the inner transition elements or inner transition metals. Okay, so we can take a look here. The white boxes on our periodic table are representative. Those are S and P block elements. Our yellow block here is our D block, known as the transition metals. And then on the very bottom of the periodic table, F block, are the rare earth metals. So let's talk a little bit more about some of these grouped elements. So natural elements, okay, are known as elements numbered 1 through 92. And again, that's our atomic number that we're talking about. And these are found in nature in their pure form or in a combined form and having reacted with something at some point. So for example, a combined element such as sodium metal combines with other elements due to its high reactivity. We don't find sodium metal in its pure form in nature, but we do find sodium atoms combined with other elements such as chlorine and things like that. Our natural elements also are the most abundant in the universe. So a few of our elements that are the most abundant, and we're talking about the entire universe. Remember, if you know from some other science classes, stars and things are made of mostly hydrogen. So 76% roughly of our universe is composed of the element hydrogen. Next is helium at about 23%. So if those two elements make up about 99% of the elements in the universe. Doesn't leave us a whole lot of room for the other elements, just kind of give you an idea of the amount of hydrogen and helium in our universe. So the most abundant element that's in our Earth's crust, okay, is quite a bit different from that. Okay, actually almost half of the Earth's crust is actually made of oxygen. So the oxygen reacts with other elements to create other compounds and things like that. 25.8% roughly is silicon, 7.5% aluminum, and about 4.7% iron. So quite a bit different. Again, a couple of these are metals and things like that, but they react with some other elements. And calcium 3.4%. So those are the 5 most abundant elements in Earth's crust. The rarest natural element, so the rarest element that we can actually still find in nature is astatine, and we think there's roughly about 28 grams of it in its entirety in nature. So not very much of that. It's fairly reactive. The transuranium elements, okay, are the elements numbered 93 and up. So atomic numbers 93 and up are the transuranium elements. And many of these are prepared in a lab and prepared from other elements. So we force them to undergo a reaction. They don't necessarily occur in nature. At least we haven't found them. And so usually these are elements that are synthesized and added to the periodic table. They are highly radioactive. That is why they don't occur so much in nature. They don't always want to stay in their form. And so those will radioactively decay into other elements. After element 103, they're so radioactive they might only exist for a split moment in time. For example, element 98, californium, okay, very expensive element. Again, these are processed often in labs. The cost of californium is $1,000 per microgram. You might wonder, well, why would somebody pay that for an element? Well, it's something that we can study and learn a lot of different things about. So that's the most expensive element. If we were to convert that, that would be $350 billion per pound. So, all right, so let's take a look at some of the classes of elements on the periodic table. There are two general classes. The first one we're going to talk about is metals. Okay? A majority of the periodic table and the elements located on it fall into this general class. And the other one we'll talk about are non-metals. Okay? So let's take a look at metals. There's a number of characteristics of metals. You may already know a number of these, but the metals are able to conduct electricity and heat. So they have conductivity in these two forms. So iron, aluminum, copper, you may already know some of those as being able to conduct electricity as well as heat. They are also malleable. For example, aluminum can be rolled out into sheets and flattened for making aluminum cans and aluminum foil, a lot of different things like that. So they have a luster. Okay, a luster gives it that shine or that sheen. It makes it so that it reflects light well. Okay, known as luster. Some might have to be polished. So if you notice, if any of you have ever had to polish your family's silverware before a meal or something like that, often those metals can become oxidized, meaning it reacts with oxygen in the air and then loses some of that luster. It's no longer a pure metal at that point. A couple examples of that would be silver and copper. Metals often are also ductile, meaning it can be drawn into a wire, similar to copper, aluminum as well, often used for wire, for electrical wire and things like that. And they're also tenacious, meaning they don't easily stretch. Okay, so let's take a look at a couple of the groups of metals. So group 1A, the furthest group on the left of the periodic table, is known as the alkali metals. So a couple of those metals on top, right underneath hydrogen there. So lithium, and those are very reactive metals. Okay, lithium, sodium, very reactive, especially with water, things like that. So they oxidize very easily. They're not found in nature unless they've been reacted with another element. Okay, they're combined with something else. So not found in their pure form. And as I mentioned, very violent reactions with water. In that reaction with water, the metal becomes oxidized and it releases hydrogen gas. In that reaction, you get the hydrogen gas, which can be very explosive, and then a metal hydroxide or base. So that's how you get like sodium hydroxide and different things like that. Most of those alkali metals are very soft. If you ever get the chance to handle any of those, lithium, sodium, very, very soft metals. You can actually bend them by hand, even cut them with a knife. Okay. and they have a very low melting point. Okay, a very low melting point. Also, good conductors. However, a number of those metals are not used for um, wire in homes and things like that because of their high reactivity. So again, group 1A, okay, those alkali metals, far left. So in the red there, right underneath hydrogen, are those alkali metals. Let's take a look at another group. So group 2A are the alkaline earth metals. And the alkaline earth metals are the group right next to those alkali metals. They're also very reactive, so they're not found in their pure form, instead found reacted with other elements. Okay, they are also highly reactive with water. So potassium reacted with water will then also create hydrogen gas and potassium hydroxide base. So just same as the alkali metals there. These are typically extracted from mineral ores, so we can mine these and extract these alkaline earth metals. And because they're so reactive, they tarnish fast as well. Oftentimes these have kind of a gray luster. Again, tarnishing fast, so they oxidize very easily, so they can lose a lot of that luster as well. So that second group there in the blue boxes here on the periodic table are the alkaline earth metals. Let's take a look at some non-metals. So we've looked at a few of the metals. There's a lot more we can look at there, but for now, let's take a look at some of the non-metals. And the non-metals are all going to be found over in P block. And the characteristics of non-metals, well, they're going to be opposite of metals, okay? So they are poor conductors. They are very brittle as a solid. Okay, some of those elements like sulfur. Okay, sulfur very brittle. They are not ductile. They're also not malleable, so they can't be drawn into a wire and they can't be flattened into sheets or rolls. So we'll take a look at one of the groups here. So group 7A is the halogen. Okay, and these are all non-metals. So it's the second to last group on the periodic table. Astatine at the very bottom, again, we think there's only about 28 grams on Earth at any time. And so we don't know a whole lot about it because it is so reactive. The far right group, 8A, is known as the noble gases. And the reason they're called the noble gases, these are hydrogen, helium through radon, is because they're not very reactive. They're inert. In fact, they have no chemical reactivity. They're pretty happy just the way they are. So we call those the noble gases. They're noble. They stand alone and don't react with other elements. Okay, completely stable. So our halogens in the orange and our noble gases on the far right. So helium through radon on the far right there in green. So one other class of elements that we haven't talked about yet are called metalloids. And metalloids are non-metals, but they also share some metal-like properties. So they follow a zigzag line on the periodic table. I'll show you here in a moment. So these elements are found on either side of the line. We can list them out here: boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and we think astatine, even though we haven't gotten to study it a whole lot. We believe that falls into the metalloids category, and it's these black boxes here on the periodic table. So this line, if we draw this line for the metalloids, on the left side is going to be our metals, on the right side is going to be our non-metals. Okay, so just know that that line there, if we follow that zigzag on the periodic table, anything to the left is a metal, anything to the right is a non-metal. So a couple trends that we talked about. We've gone over a couple of these already, if you remember from some of the work that we did in our last lesson. But one thing I want to look at here is atomic radius. So atomic radius as we go across periods. So it decreases as we go across. When we get from the left side to the right side, that right side holds on to those electrons a lot tighter, a lot closer. If you remember, they also have higher ionization energy, meaning it's harder to take those electrons away. So they hold them much closer, which tends to give them a smaller atomic radius. Okay, there's also more protons. Those more protons in the nucleus is going to have a greater attraction to those electrons and hold those closer. Okay, so holding those electrons tighter give it a smaller atomic radius as we move left to right across the period. The groups for related to atomic radius, okay, the atomic radius increases as you go down a group. Okay, due to the fact that the electron levels are added as you go down, right? We're adding more electrons, we're adding more energy levels, so those electrons now are spaced further out away from the nucleus, is going to give it a greater atomic radius. So I hope that this was helpful for you guys. If you have any questions about any of this stuff, please don't hesitate to send me a message or a comment, and I would be happy to go over any of that stuff with you guys. So I hope this was helpful, and I will see you guys in the next one. Thanks.